Okay. um, the last one, I think. Yeah, the last one. Okay, so let's talk about. So we've talked about real distinct roots, and then complex roots, complex conjugate pairs of roots. And then of course, you can see that the combination of the two we can handle. You just treat the real distinct roots first, and then take care of complex conjugate roots. All right. Now we're going to talk about real or repeated roots. Okay. So first thing I want to remind you of. Okay. So a few things I want to give you a reminder that we've already done. If I take the Laplace transform of a step, and I'll say u of t, that's in this specific case that's a step. If I do the Laplace transform pair, you should remember that it's 1 over s. Okay, constant, and then 1 over s. Okay, and then you should remember this. If I take the integral of f of tau d tau, that is equal to 1 over s times f of s. Okay, which is of course f of s again is the Laplace transform of f of t by definition. Okay, so we've already also shown what the Laplace transform of t is. Okay, t is Laplace transform of t u of t is equal to 1 over s squared. Okay, and 1 over s squared by itself. All right, because we use this little trick to find that, and then again, and that's the ramp. Okay, so that's the ramp function, and then of course also another Laplace transform pair would be 1/2 t squared u of t, and this was your workshop. Okay, was 1 over s cubed. Okay, and of course if it was we did just t squared, so you have to multiply 2 over here and you get 2 over s cubed was the solution to the workshop. All right. Now I also want to remind you of the frequency shift. Okay, so let's continue. Don't forget, again, this is just review because we've already seen these, but the frequency shift, which is the Laplace transform of e to the minus s naught t, so e to the something t times some function, f of t, is just equal to f of s plus s naught, where you replace f of s, you replace s with s plus s naught. Okay, so one example would be t times e to the minus at times t times u of t. Okay, so this is like, there's s naught, okay, is a, and t u of t is your function. We know what f of s is for that, right? For t, if I go back, Laplace transform of t is, or t times u of t, is 1 over s squared. Okay, so that's equal to 1 over s squared, but then we substitute for s, we substitute s plus s naught, or s plus a. So I can plug it in, and you have s plus a squared. Okay, so now you have another, using the Laplace, you have another Laplace transform pair that we can put together. All right. So what I can do is I can take all of these, and I want to take a subset of the Laplace table, and I want to make our own table here. And the purpose of it is to see a pattern. Okay. So for example, t e to the minus at is 1 over s plus a squared. All right, that was that. I just brought the t out on purpose. All right, so we'll see why. Then we can also generalize it. If I have t to the n, e to the minus at over, turns out over n factorial, over n factorial, then that is equal to 1 over s plus a to the power n plus 1. Okay? And let's do another one. How about t times sine of omega t? Well, the Laplace transform of that is 2 omega s over s squared plus omega squared, quantity squared. All right? And then actually one more I want to do, okay, one more, is t e to the minus at sine of omega t becomes 2 omega s plus a all over quantity s plus a squared plus omega squared, all quantity squared. Okay, so here's the pattern I want you to see. Now you can look all of these up, or most of them, in that Laplace transform table. But I want you to see is that if you see a t, remember if I block t, like get rid of t here, then what is the Laplace transform of this? Well, I hope that you can see you get rid of squared. Okay, so if I add t, I have to put squared. So here's what you see. By adding t, you get a repeated root. All right, this is a repeated root. This is s plus a times s plus a. That's a repeated root. All right, let's look over here. If I multiply t n times, I get n plus 1 repeated roots. Okay, or repeated roots n plus 1 times. Okay, let's look over here. Let me jump over to this one. If you remember, if I take away the t, then I take away this squared, and I also take away, let's see, I guess it would be, I'd have to go back, but maybe this 2 omega or the s plus a, one of them. It's a little bit trickier, but if I focus on the denominator, if I add a t, then I add a square. All right, so I hope that you see that multiplying by t gives you a repeated root, or a repeated root, if I take the inverse Laplace transform, you know you're going to get a t. All right, so that's what I want you to, really kind of see from all this. All right, so let's do an example of a problem with a repeated root. Okay, so let's do x of s equals s plus 3 all over s squared plus 2s plus 1 times s plus 2. Well, that actually turns out to be s plus 3 all over s plus 1 squared times s plus 2. Okay? So, here is how you do the partial fraction expansion for repeated roots. Well, I have one repeated root that is repeated twice, and then one distinct real root. So we already know how to write the distinct real root. I'm just going to write a over s plus 2, done. All right. Now, for the repeated root, I'm going to write b over s plus 1. Okay, nothing's changed there. That would be the same as if there was no squared there. But now I'm going to add a new term, c over s plus 1 quantity squared. And I'll put the 2 back up. Now, can you guess what would happen if I had an s plus 1 quantity cubed? All right. If you guessed that you would get a d over s plus 1 quantity cubed, then you're correct. Okay. So for every repeated root, you have to start from to the power 1, power 2, dot, 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 all the way to the power n. Okay. Hold on. Okay, sorry, I got distracted there for a second. Okay, so I'm going to erase that, just so you can see, and we're back to the original problem. Okay, so I'm going to write down that as a rule, if s plus a to the power n are repeated roots, the partial fraction expansion will include the terms s plus a, s plus a squared, dot, 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 all the way to s plus a to the power n. All right? Just what I was trying to say up here. So once we have that knowledge down, we can now we just need to, again, solve for a, b, and c. And we can easily do the inverse Laplace because we have these for every table. In fact, let me write that down. Let me say x of s equals s plus 3 times s plus 1 squared s plus 2, which is equal to a over s plus 2 plus b over s plus 1 plus c over s plus 1 squared. Okay. Now, let's find, well, first of all, hopefully you can see that x of t is going to be, well, a e to the minus 2t, b e to the minus t. Okay, that's obvious. And then now, hopefully you can see that this is the same as c over s plus 1, which is e to the minus t again, but multiplied by 1t because of the repeated root. So t e to the minus t. Okay, so don't forget about that t. If you see a t, that's due to repeated roots. Okay, all right. So let's find a, b, and c. Well, a is easy. A is a distinct real root. I'm just going to go multiply s plus 2 times x of s and evaluate at s equals minus 2. So that is going to be s plus 3 over s plus 1 quantity squared. Evaluated at s equals minus 2. That gives you 1 and 1. Okay. Now, this side, I'm just going to get, well, I'm just going to get a. So that's it. Done. A. All right. So a is easy because it's a distinct real root. Now, b and c, now the question is, can I do the same? What happens if I try to find b equals s plus 1 times x of s, evaluate s equals minus 1? Watch what happens. All right. Yeah, this will go to 0. This will be b. But what happens here? You only cancel one of these s's, and that leaves you an infinity because when you plug in s equals minus 1, that's 0, or undefined if you want to say that. Okay, so that doesn't work. But guess what does work? What does work is if I multiply by the highest order. This is the only one that'll work that way, is the highest order. Okay, so if I had n repeated roots, I could multiply by the nth, okay, and that'll give me c, and evaluate at the root. I can do that. Okay, so let's go ahead and do that. So that's s. So I'm going to multiply this portion here, which will give me s plus 3 over s plus 2. Evaluate at s equals minus 1. That is equal to 2 over, so you get 2. All right, so that's, did I do something wrong? Oh, no, I'm not done yet. No, wait a minute. Let me double check. What is... Oh, yeah. Okay. So, so that's it for C. Done. All right. Finally, we're left with B, and we can't do that trick of multiplying s plus 1 because we'll get it undefined over here. So what I'm going to do is use my other trick and evaluate, okay, at some root that's not one of the, some s value that is not one of the roots, so 0 will work fine. Okay, so I'm going to get, well, if I plug in 0 over here, I get 3 over 2 is equal to a over 2, which is 1, so 1 over 2, plus b plus b, and then plus c, which is 2. Okay, because this becomes 1. All right. So if I multiply by 2 on both sides, I get, or or I'll just subtract a half and then subtract 2, which will give me b equals minus 1. Does that make sense? I think that makes sense. B equals minus 1. Okay? So that's it. Now I plug it back into the values, and I get x of t equals minus e to the, where's a? Yeah. Oh, wait. Oh, yeah. Equals e to the minus 2t plus, which is minus, actually b is a minus 1, so minus e to the minus t, and then c is 2, so plus 2t e to the minus t. And we're done. Okay? So that is the trick. Let's see. All right? See if I think that that completes this lecture. All right? So let me just recap what we did. What we did is we took a differential equation, took it into the Laplace domain, okay? Then used algebra, okay, to solve for the output, or either x of s or whatever the output variable is, okay? And then took x of s through partial fraction expansion to clean it up, and then that way we can use tables, so P of E. Then we were able to use tables to do inverse Laplace to get x of t. Okay, so we had this sort of pausing point where we did some manipulated x of s using partial fraction expansion into blocks that we can use to do a lookup. So this is our lookup table. And we just did the inverse Laplace to get x of t. Done. Okay? We had a few different cases. Specifically the roots of the denominator mattered. Okay? Our first case was distinct real roots, complex, distinct, and of course the final one is repeated. Okay. I will send this out to you guys.